Okay, problem 2. We've got at time t equals 0 a 750 gram mass at the end of a horizontal spring with a spring constant of this is struck by a hammer giving an initial speed of this. So what gives it the initial speed really is not important. What matters is that it has some initial speed. So it has an initial speed v naught that way. And there's a known spring constant to this guy, and it slides horizontally. So we'll just go, and I guess it says a horizontal spring. We're going to assume that if it's on a surface, it's frictionless because they don't, they don't mention that. Okay, so and it's got initial speed that we know. So the tricky thing here, let's see, which one do I want to do? Position, function of time, total energy of the system. So, easiest thing probably actually is total energy. So why don't we do total energy first? We're going to do E first. I'm going to do an orange. Okay, total energy of the system. So, like we learned in the previous problem, total energy, or sorry, there we go, E mech, mechanical energy, total energy, is potential plus kinetic. And from the difference between capital K for kinetic energy and little k for spring constant. Okay, so and this is even easier to see because there's no gravity to confuse us. So let's just say that this direction, we're going to call this positive x direction, and so the potential energy is U is 1/2 k x squared, and kinetic energy is 1/2 mv squared. So initially, come on, stupid pen. Okay, initially, x is 0 because we're starting at rest, and we're using our x is 0 as our rest position. That's what we always do with simple harmonic motion. Just makes things easier. And then your speed is this v naught we had. So initially then potential energy is 0 and kinetic energy is 1/2 mv squared, or 1/2 mv naught squared. So initially we're at the equilibrium position and we get this smack from a hammer and get going this way to the right with the speed v naught, and that means initially our kinetic energy is this. Sorry, I'm at the equal sign there. Potential energy is 0. So the mechanical energy is 1/2 mv naught squared, and v naught we were given this here is v naught, and we have the mass, so that's all there. So that's all great. Let's see now what is next. We need to find period and frequency, we need amplitude, we need maximum acceleration of the system, and we need position as a function of time. Let's go with amplitude next, because when we do position as a function of time, we need amplitude for that. And that's just, amplitude we can get fairly easy from energy considerations again. So let's go dark brown for B. And B, when it's at the amplitude is the the distance, or the furthest distance it gets from the equilibrium position. And when x equals the amplitude, positive amplitude or negative amplitude, whichever one you want, that means your speed is 0. And so we can really solve this with energy again, because by taking this E mech equals U plus K and taking E mech is going to be potential energy 1/2 kx squared plus 1/2 mv squared. We know that already. Okay, and so we know that when x equals a, v equals 0. So that's when it is at its most, or the furthest point from equilibrium. So, and that when that happens, kinetic energy goes away. So we can actually just say E mech equals 1/2 k, and then when x equals a, ka squared. And this term goes away because v equals 0. So that means then we can do 1/2 k a squared, and emec, we also solved it here in terms of this initial speed, v naught. So we can actually put these two together and say 1/2 m v naught squared equals 1/2 k a squared. And my a looks a little strange there, so let's try that again. A squared. And then we have, it works out very nicely, because then you can cancel the 1/2s. So let me get my red canceling. Ah, come on, stupid pen. There we go. Come on. There we go. And then what you can get, let's see, we wanted amplitude. So amplitude squared equals, let's say that's going to be m over k times v naught squared. And m over k, you might recall, from previously that omega squared is k over m, right? So what that tells us is, putting this together with this term, this whole thing gets us a squared equals v naught squared over omega squared, because omega squared is k over m. Here's your m over k, so that all works. And then we can get our amplitude finally to be a is v naught over omega. And we can already solve for omega from, well, we know k, we know m here, there's m, and we know k. So we can already solve for omega. So that gets us omega equals square root of k over m. So you just plug in your k and your m there. And so that nicely gets us then, this gets us the answer to part B, which actually I was doing in brown and I changed to red, but whatever. We can also find the period and frequency. So you recall omega equals 2 pi f. Oh, come on. Let's see. Omega equals 2 pi f. Okay, so what that means then is we put these two together, and you should get the frequency equals, let's see, it's going to be omega divided by 2 pi, and this is our omega here. So square root of k over m divided by 2 pi. And that's going to be our frequency. And then, of course, we can get period is just 1 over frequency. Okay, frequency is number of cycles per second, and period is the number of seconds per cycle. So that gets us A. We have A, B, and E. C and D are not terribly hard. So one thing we can look at here is, let's see, for D, for position as a function of time, let's look at that. D. We now have x equals, we know the amplitude. Do we want to pick sine or cosine? Well, which one starts at 0 at time equals 0? Because we're starting at rest at the equilibrium position. So which one starts at 0 at time equals 0? The answer is sine. And so we have a sine omega t, where omega is this here. So that actually answers part D for us entirely, because we know what omega is, we know what a is. We solved for a down here. So that takes care of D. Oh yeah, and then the other thing you have to check with these is, are you going in the right direction initially? So we said initially your initial speed was going in the positive x direction. I guess they didn't tell us here, so we could have chosen either x equals positive a sine omega t, which we did, or we could have chosen x equals negative a sine omega t. Either one would have worked, but in this case, for the diagram I did, positive is correct. Okay, so, So, part C now, maximum acceleration of the system. So let us look then. Now there are two ways to do this. One is to go with calculus and just take two derivatives of x and then get to a equals omega squared, whatever. The other way to do it is to just look at, well, it's going to be undergoing its maximum acceleration when the position is the furthest distance from here. So recall F equals ma, right? So we're going to have maximum acceleration when the force is maximum. And the force due to a spring is negative kx. So ignoring the fact that it's negative, what we're looking for is simply what's the acceleration when x is at a maximum, or, well, it's either at a positive extreme or a negative extreme, and a equals, yeah, I'm really not terribly thrilled with this. There we go. A equals a max when x equals positive or negative a, the amplitude, capital A amplitude. So watch out for the difference between little a acceleration and big A amplitude. But when you have that, then what you get, f equals k times amplitude, and that's going to equal mass times little acceleration. So then, and that's going to be your maximum acceleration, little a acceleration. So let's see, where can I put this in? A max is going to equal k over m times your amplitude. Try that again. That's a little better. And that is answer to part C. So again, with these things, on the test, we're not going to make you answer 5 of these things. We're probably going to ask you about 2 of these questions, but they do all interrelate, and sometimes it's useful to solve one, before the others, or solve them out of order. Okay, I will move on to problem 3 next.